Architecture is the union of strength and beauty. From the 43.3-meter dome of ancient Rome to modern skyscrapers rising 828 meters into the sky, every landmark carries within it an engineering miracle. Now, step into the world's 10 most astonishing mega projects and uncover the engineering intelligence and aesthetic mastery that have shaped human civilization across thousands of years. Above the rippling blue waters of Sydney Harbour in Australia, a cluster of buildings shaped like pure white sail slices cleanly into the sky. This is the Sydney Opera House, an architectural miracle that brings together the precision of engineering structures and the fluid grace of artistic form in perfect balance. From the very moment of its conception, this building was a bold act of defiance against architectural convention. A true engineering gamble that challenged everything considered safe and practical at the time. Architect John Daxing drew inspiration from the natural curves of seashells along the shoreline, deliberately abandoning rigid, rectangular architectural forms in favor of an extremely demanding system of prefabricated concrete shell structures. Under the technological conditions of that era, such a design was nothing short of revolutionary. Each shell was not a simple circular arc, but a complex composition formed from multiple parabolic curves. To turn these curves into physical reality, engineers faced immense challenges: ultra-precise prefabrication, tight structural tolerances, and reliable sealing between every single component. Their solution was both ingenious and labor-intensive. The massive curved surfaces were broken into hundreds of prefabricated concrete segments, produced in factories and assembled on site, with steel cables pulled into place with extreme precision. Inside, the concert halls and theaters rely on the geometry of these shells to produce sound fields that are evenly distributed and remarkably clear, while maintaining structural stability. These brilliant white thin shells are not merely visually striking. Their true strength lies in the precise interlocking of each concrete component and the careful balance of forces hidden within the structure. The beauty of the Sydney Opera House lies in its seamless coexistence with its natural surroundings, reflecting the sea, the sky, and the movement of the harbour itself. As one of the defining architectural masterpieces of the 20th century, the Sydney Opera House transformed engineering breakthroughs into architectural poetry, proving that engineering and art are not opposites, but extraordinary partners when they truly merge. Standing quietly at the heart of ancient Rome, the Pantheon has endured for nearly 2,000 years, outlasting empires, wars, and the rise of modern cities around it. From the outside, its appearance is almost restrained, revealing little of the engineering achievement hidden behind this seemingly ordinary classical facade. Step inside, and the scale is immediately revealed. A concrete dome spanning 43.3 meters, a record that would stand unmatched for more than 18 centuries. Reaching this moment required extraordinary effort, from transporting massive granite columns across the Mediterranean to assembling them without modern machinery. Although parts of its original materials were later removed and reused elsewhere, the dome itself remained structurally uncompromised. The interior served both religious and imperial purposes, blending sacred space with political authority under a single architectural vision. Every recess and opening within the thick walls played a structural role, helping distribute immense loads while reducing unnecessary mass. At the apex of the dome, a single circular opening becomes the building's only source of natural light, allowing the sun to trace time across the interior. Counterintuitively, removing material at the crown strengthened the structure, locking the forces of the dome into perfect balance. The geometry is deliberate, a sphere resting on a cylinder, transforming abstract ideas about order and the cosmos into built space. The stepped coffers carved into the dome reduce weight while extending the structure's lifespan, combining beauty with engineering necessity. As the dome rises, the concrete itself becomes lighter, heavy stone below, porous pumice above, preserving strength while easing the load. Its conversion into a church ensured its survival, allowing the Pantheon to endure while countless other ancient structures disappeared. More than a Roman achievement, the Pantheon became a timeless reference, shaping dome construction throughout architectural history. Stretching across the Tarn Valley in southern France, the Millau Viaduct spans 2,460 meters, carrying nearly 290,000 tons of steel and concrete high above the landscape. It is one of the most ambitious bridge projects ever attempted, and one that redefined what modern engineering could achieve. The idea took nearly 17 years to move from concept to reality. Architect Norman Foster and structural engineer Michel Verlejeux joined forces to confront a challenge no bridge had faced before: supporting a roadway on pylons rising up to 245 meters above the valley floor. Everything began underground. Each foundation was driven 18 meters deep into unstable terrain, using massive elephant, foot-shaped bases and inclined shafts designed to resist landslides, seismic forces, and the extreme winds that sweep through the valley. The bridge piers were then built upward using self-climbing formwork. Every 3 days, each pier rose another 4 meters, allowing 7 towering supports to grow simultaneously, slowly transforming concrete into structures as tall as skyscrapers. At a height of 90 meters, each pier splits into 2 slender columns. This design was not aesthetic alone, it allows powerful winds, sometimes exceeding 100 kilometers per h-hour, to pass through the structure rather than tear it apart. To cross the widest spans of the valley, engineers erected temporary steel towers over 200 meters high, anchoring them to sheer cliffs. These structures supported one of the boldest construction strategies ever used on a bridge of this scale. The steel deck was pushed into place using 64 synchronized hydraulic systems, each controlled with millimeter precision. Over 3 days, the roadway advanced 1971 meters, with virtually no margin for error. Above the deck, 7 steel pylons, each weighing around 700 tons, were lifted into position using a method inspired by ancient obelisk construction, carefully rotated and raised into place with modern precision. From these pylons, 154 steel cables now support the deck, collectively bearing more than 360,000 tons. Each cable is designed for immense strength, yet engineered with a limited service life to ensure long-term safety. Seasonal temperature changes cause the steel roadway to expand and contract by nearly 2 meters. Hidden expansion joints and constant monitoring allow the structure to move freely without compromising its integrity. Inside the bridge, a dehumidification system keeps humidity at a constant 45%, protecting the steel from corrosion and reducing maintenance costs by millions over the bridge. As lifespan, even the slight curve of the roadway was intentional, offering drivers a clear view across the entire span and enhancing both safety and visual impact as the bridge reveals itself all at once. Completed in just 3 years after more than 800,000 hours of work, the Millau Viaduct stands as a rare moment when bold calculation became lasting reality, and engineering doubt was replaced by undeniable proof. For over 135 years, this building has remained unfinished, not because it failed, but because its ambition outpaced its era. Rising from Barcelona's rigid grid of straight streets is something entirely different, a structure that appears less designed than grown. In an age without computers or CAD software, Antoni Gortu turned gravity itself into a design tool. By suspending strings and weights, he allowed natural forces to define structure, revealing forms that distribute load with perfect efficiency. Then history intervened. War erased drawings, models, and plans, leaving behind one of the most complex architectural puzzles ever attempted. As construction resumed, even the original stone ran out, forcing engineers to search the world for materials that could match Gortu's vision. A turning point arrived when modern modeling software finally translated Gortu's organic logic into buildable reality. Inside, stone columns branch like trees. Light flows like leaves overhead, creating a space that feels less constructed than alive. Here, engineering, nature, and faith converge, a stone forest still growing within the modern city. Linking Manhattan and Brooklyn across the East River, the Brooklyn Bridge would become a turning point in bridge engineering and the future of New York City itself. By erasing the physical divide between two growing cities, the bridge reshaped transportation and helped give birth to modern Greater New York. Before its construction, ferries were the only connection, unreliable, dangerous, and often paralyzed by ice and storms. The vision belonged to engineer John Roebling, who believed steel wire cables could conquer the river where nature had always prevailed. Rather than relying on stone or timber, Roebling pioneered the use of steel wire cables, weaving thousands of fine strands into elements of unprecedented strength. His design combined industrial innovation with Gothic architecture, using massive stone towers to anchor the forces carried by the steel cables above. The decision to trust steel as the primary load-bearing material marked a decisive break from traditional bridge construction and quietly set a new global standard. Tragically, John Roebling would never see the bridge completed, leaving the task to his son, Washington Roebling. During construction, engineers faced one of the greatest challenges of the project, building massive foundations underwater. To overcome this, they pioneered the use of caissons, enormous airtight chambers that were sunk to the riverbed, allowing workers to excavate and pour foundations beneath the waterline. This innovation made it possible to anchor the bridge securely in the depths of the East River. The strength of the Brooklyn Bridge lies in the combined power of its steel cables and monumental stone towers, engineered to withstand powerful currents and relentless winds. Its beauty, however, comes from contrast. The Gothic arches of its towers, paired with the clean, sweeping lines of steel suspension cables. Together, they fuse the raw force of the industrial age with classical architectural elegance, transforming the bridge into one of New York City's most enduring and iconic landmarks. As one of China's most ambitious modern megaprojects, Beijing Daxing International Airport emerged in just 5 years, stunning the world with both its scale and speed of construction. Faced with overwhelming congestion at the existing airport, China made a decisive choice to build an entirely new aviation hub designed for the future. The terminal adopts a radial star-shaped layout spreading outward from a central core to maximize efficiency, while minimizing walking distances for passengers. Behind this form lies extreme precision, where large-scale prefabrication and millimeter-level coordination allowed construction to be completed far faster than traditional timelines. The star-shaped plan also reshapes the passenger experience, reducing travel distances and enabling fast technology-driven movement through the terminal. By concentrating operations into a single terminal, transfer efficiency increases dramatically, setting a new benchmark for large international airports. Covering more than 1.4 million square meters, The terminal combines structural ambition with operational clarity, earning recognition far beyond its national borders. More than an airport, Beijing Daxing stands as a statement of modern Chinese engineering, where scale, efficiency, and human-centered design converge into a single integrated system. Rising from the Champ de Mars in Paris, the Eiffel Tower stands as a bold declaration of the industrial age, built not from stone, but from exposed steel and structural logic. Today, it is a symbol of romance. Yet when it first appeared, many artists and intellectuals condemned it as a steel monstrosity unworthy of Paris. While critics debated aesthetics in Parisian cafés, hundreds of workers were already committed to an unprecedented engineering challenge. In just 2 years, thousands of prefabricated iron components were assembled high above the ground, connected by millions of rivets without modern safety equipment. Remarkably, the project recorded an unprecedented level of safety for its time, a result of meticulous planning and structural precision. As the tower rose above Paris, surpassing every historic landmark around it, opposition gradually gave way to awe. Originally intended to stand for only 20 years, the tower soon faced dismantling until its true value began to reveal itself. Its height made it indispensable for scientific experiments and wireless communication, ultimately securing its survival during wartime. Even in occupation, the structure became a silent act of resistance, refusing to serve power without effort. Carefully maintained and constantly adapting to temperature and wind, the tower continues to stand through engineering intelligence rather than sheer mass. Once dismissed as temporary and unwanted, the Eiffel Tower ultimately transformed structural logic into one of humanity's most enduring symbols. At the very center of Beijing's Forbidden City rises the whole of supreme harmony, the ceremonial heart of imperial power for nearly 5 centuries and the highest-ranking structure of the entire palace complex. Even today, much of this imperial complex remains restricted, preserving layers of history that once governed coronations, state rituals, and the authority of the throne. Constructed during the Ming Dynasty, the whole demanded vast resources and human labor, reflecting not only architectural ambition, but the absolute concentration of imperial power. For emperors, the whole of supreme harmony was not merely a building, but a political instrument, a stage designed to project cosmic order, legitimacy, and control. Despite repeated destruction by fire, the whole was rebuilt again and again, demonstrating the resilience of its underlying structural system. At the core of this resilience lies an extraordinary timber framework, assembled entirely without metal nails, relying instead on precise mortise and tenon joints. This interlocking system allowed the massive wooden columns and beams to function as a single organism, distributing loads efficiently while absorbing seismic forces over centuries. Above this structure rises a double-eaved hip roof, the highest status roof form in traditional Chinese architecture, reserved exclusively for supreme imperial authority. Its yellow glazed tiles, ridge beasts, and strict decorative hierarchy reinforced a political order where architecture itself became an instrument of governance. Every proportion, ornament, and structural rule followed ritual law, binding political authority, cosmology, and architecture into a single system. As dynasties declined, the whole remained, its structure outlasting the very power it was built to serve. More than a symbol of empire, the whole of supreme harmony stands as the highest achievement of traditional Chinese timber engineering and architectural wisdom. dominating the skyline of Dubai. The Burj Khalifa rises to an unprecedented height of 828 meters, redefining what modern engineering believed possible. The challenge began beneath the sand itself, where engineers were forced to confront unstable ground and design a foundation capable of supporting an extreme vertical load. By combining a massive reinforced concrete raft with deep friction piles, the structure achieved remarkable stability, limiting settlement to only a few centimeters. As the tower rose, wind became the dominant threat, forcing engineers to abandon conventional forms and rethink how a skyscraper interacts with the atmosphere. A tapered, Y-shaped plan emerged, disrupting wind vortices and unexpectedly allowing the structure to climb even higher than originally planned. Inside, the tower functions as a vertical city, supported by high-speed elevators and a layered transportation system that moves people efficiently across extreme heights. To survive extreme desert heat, the Viaduct combines high-performance glazing and advanced coatings to reduce solar gain while maintaining transparency. Every system inside the tower, from climate control to lightning protection, reflects the same principle: integration, resilience, and control at an unprecedented scale. More than a record-breaking skyscraper, the Burj Khalifa stands as a symbol of modern ambition, a structure that transformed technological innovation into vertical form. Crowning the Acropolis of Athens, the Parthenon stands as one of the most influential architectural works in human history, embodying the classical ideals of harmony, balance, and rational beauty. What appears perfect is, in fact, carefully corrected. Columns lean inward, shafts subtly swell, and no line is truly straight, all to counter the limitations of human perception. Built in 432 BCE to honor the goddess Athena, the Parthenon emerged from a deliberate political and cultural decision to express power, order, and civic identity through architecture. Every sculptural element was integrated into the architectural system, combining myth, ritual, and proportion into a unified visual language. Behind its serene appearance, the Parthenon also functioned as a symbol of economic and political authority, tightly bound to the power of the Athenian state. Over time, political upheaval stripped away its material wealth, while the structure itself remained a silent witness to changing regimes. Thank you for watching. See you next time.